the interesting consequences of mean value theorem or Rolle's theorem is that it allows us to prove what is a slightly weaker of the version of the fundamental theorem of calculus. So, example, show that any polynomial of degree n has at most n roots. And we can do this by induction. Okay, so by induction, base case, n is equal to 1, x minus a has only one root, x is equal to a, right? X minus a is equal to 0, has only one root, x is equal to a. Therefore, true for n is equal to 1. Therefore, true for n is equal to 1. So let us assume it's true for n is equal to k. Therefore, assume for n is equal to k. Show for n is equal to k plus 1. Show for n is equal to k plus 1. So I'm going to assume that the theorem holds for n is equal to k. Suppose the polynomial of degree n plus k plus 1 has k plus 2 roots. Suppose a polynomial f of x of degree k plus 1 has k plus 2 roots. Call them a1, a2, all the way up to ak plus 2, right? So I have these k plus 2 roots. Then f of a1 is equal to f of a2 is equal to dot 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 is equal to f of an not n k plus 2 is equal to 0. Therefore, as it's a polynomial, it is differentiable everywhere. Therefore, f prime of x, therefore, by Rolle's theorem, there are k plus 1 numbers. There are k plus 1 numbers b1, b2, bk plus 1 such that bi lies between ai and ai plus 1. Bi belongs to ai comma ai plus 1, and what am I trying to say? Yes, so and f prime at bi is equal to 0 for every I, right? Therefore, f prime of x well, we know how to take derivatives of polynomials, is a degree k polynomial polynomial with k plus 1 roots, with k plus 1 roots, which are b1 to bk plus 1. Contradiction. Contradicting the assumption that the result is true for n is equal to k. Assumption that the result is true for n is equal to k. Therefore, by contradiction, therefore, f of x has at most k plus 1 roots. Therefore, true for n is equal to k plus 1, and therefore the result has to be true for every n. Therefore, any n degree polynomial has at most n roots for every n in naturals. Okay, so that's my first example using Rolle's theorem. Now let us do some more maybe sort of interesting results. Okay, so we saw up to theorem 4 last time. So theorem 5, theorem 4 was my mean value theorem. Suppose f prime of a is equal to 0. If the second derivative f double prime of a is greater than 0, then f has a local minimum. And if f double prime of a is smaller than 0, then f has a local maximum at a. Okay. Proof. By the way, this is known as the second derivative test, in case you guys probably have seen this in Calc 1 or 2 before, but in case you haven't, this is called the second derivative test, and this shall from now be referred to as the second derivative test. I will be proving it only for the case that it is a maximum. Proof for maximum for f double prime of a is smaller than 0. Okay, I'll show that it's a maximum. The proof for minimum is exactly similar. Okay, so by definition, f double prime of a is f prime of a plus h, is limit h goes to 0, f prime of a plus h minus f prime of a all the way over h, right? Now, I know that f prime of a is 0. Therefore, as f prime of a is equal to 0, f double prime of a is equal to limit h goes to 0, f prime of a plus h over h, right? So this means, therefore, as f double prime of a is smaller than 0, this means when f prime of a plus when h is negative, when h is negative, f prime of a plus h is positive. And when h is positive, f prime of a plus h is negative. Right? So that means, therefore, since when h is negative, f prime of h is positive, therefore f prime f is, when f prime is positive, f is increasing. F is increasing when h is negative, and f is decreasing when h is positive. Well, if h is increasing when h is negative and decreasing when h is positive, therefore that means f has a maximum at a, right? Because if I look at the image, what is the image going to look like? Well, the function is increasing before it's a, and then it is decreasing, right? And so that means that your function is that means maxima. F double prime of a is smaller than 0, maxima. Okay, so one of my old professors had a really fun way of explaining this to remember which one is a maximum and which one means a minimum. And here was the method. F double prime of a greater than 0, therefore positive, therefore happy. And so you are going to look like this. You have a nice smile, and that means your function is concave, and that means it's a minimum. Okay. If f double prime of a is smaller than 0, then you're feeling negative, and therefore you're sad. Let's say you're feeling blue. Then you're feeling sad, and your face is going to look like this. And that's a maximum. Okay, so I found that really helpful because back in the day, I used to be extremely confused by this. I couldn't remember if f double prime greater than 0 meant in maxima or minima. I had to draw the figure every time. This helped me out. Okay. Now, unlike the result where, the first derivative being 0 does not mean that it's a maxima or minima, here the reverse is also true. Suppose f double prime of a exists. Okay. Then, if f has a local minimum at a, then f double prime of a is greater than or equal to 0. If f has a local maximum at a, then f double prime of a is smaller than or equal to 0, right? So the other way around is also more or less true. When I say more or less, that is because this one includes it being greater than or equal to, or smaller than or equal to. The previous theorem, theorem 5, has a strict greater than or smaller than, because that result is no longer true if I replace it by greater than or equal to. Okay, so be careful with that, but this is greater than or equal to, smaller than or equal to. And the proof is relatively simple. Suppose f has a local maximum, a local minimum at a. Suppose f has a local minimum at a. Well, if it is a local minimum, therefore f prime of a is equal to 0, right? We know that if it's a local minimum or a maximum, then it is 0. Then, if f double prime of a was smaller than or equal to, well, not smaller than or equal to, was strictly smaller than 0, then by the previous theorem 5, then by theorem 5, it is also a maximum. A is a local maximum. Well, that's dumb, but that means my A is a local minimum and maximum. Therefore, A is a minimum and maximum of f, right? And therefore f is constant, right? Because if it's minimum and maximum of f, the only possible way that is happening is if f was constant. Ugh, stop moving randomly. Okay. Well, what is the contradiction if it's a constant? Well, if it is a constant, then its second derivative at a should be actually 0, right? Because the first, if the second derivative is if f is a constant, then f prime is constantly 0, and so, well, if f prime is a constant, f double prime is 0, contradicting f double prime of a strictly smaller than 0, right? Therefore, f prime double prime of a has to be greater than or equal to 0 as required. Okay, once again, I am going to leave the proof of the other case to you guys. Okay? And the final result of this video is going to be theorem 7. Suppose f is continuous at a and that f prime of x exists for all x in some interval containing a, in some interval I containing a. Okay, except perhaps for x is equal to a. Except perhaps for x is equal to a. So maybe my first derivative exists for every point, maybe not for exactly this point, Okay, we have seen a counterexample of this, like the chapter 10 last example is a counterexample for everything I'm writing till now. Now, well, counterexample as an example of a function where these things hold true. Now, suppose limit x goes to a, f prime of x exists. Okay, then f prime of a exists and f prime of a is equal to limit x goes to limit x goes to a f prime of x, right? Proof. I got ahead. Let me say this. So the example that we saw at the end of chapter 10, which was x squared sine 1 over x, that function f is continuous at a, and f prime exists for all x in some interval I containing a, except perhaps for x is equal to a, right? What did not work out in that example was because this part was not holding true, right? This did not happen. F prime existed, but f prime of a was not true for f of x is equal to x squared sine 1 over x, right? This implication did not work out. It works out because I am assuming the extra condition that limit f prime of x exists. Okay, so it's an important condition. Okay, how do we prove that? Well, by definition, f prime of a is equal to limit h goes to a, h goes to 0, my bad, 0, f of a plus h minus f of a over h, right? Now, for a sufficiently small h, for a sufficiently small h, if I take h to be small enough, the function f is continuous, right? The function is continuous at a, so it has to be continuous in some interval at a. F is continuous on a comma a plus h. Okay, this is easy to see. Basically, it's the epsilon delta use the epsilon delta definition. Whatever you take as, for a given epsilon, if you find the delta to be, let's say, delta 1, take the delta on a to a plus h as delta over 4 or something, right? And it will work out. You can find from a to a plus delta, you can take the delta to be delta over 4, and things will work out for the entire thing by our standard trick. Okay, so you can find it to be continuous on that, and f is differentiable on a comma a plus h, which you can take this you can do by take h such that a comma a plus h is actually in my interval I. Right? If I take it in this, then actually this makes my life so much easier. If I do this, it is differentiable, which implies that it is also continuous on all of a to a plus h. So forget about the first part I said. Here that holds because I can take it in my interval h, right? Then, by mean value theorem, there is a number, there exists x naught in a comma a plus h such that f of a plus h minus f of a all over h is equal to f prime of f prime of x naught, right? That's my mean value theorem. Now, as h goes to 0, so maybe I shouldn't have taken this as x naught. Let me take this as let me call this AH. And the reason is this AH depends on what I'm taking as my H, right? Now as H goes to 0, AH goes to A, right? Because, my interval A plus H is getting smaller and smaller, so it's going to go to A. Therefore, f prime of A is equal to limit h goes to 0, f of a plus h minus f of a over h is equal to limit h goes to 0 of AH, and I've already said that this goes to A, right? This is equal to f prime of, well, x goes to 0, f prime of x, oh, no, sorry, this should have been f prime of AH, my bad, f prime of AH, and this goes to f prime of x, right? And, well, that is exactly equal to f prime of A because AH was going to A, right? And so you get this result. Okay, so this is a slightly, you might want to write it down slightly more rigorously or to have faith in it yourself, but it works out. Okay, I'm going to stop this lecture here. Next part we'll look at would be the Cauchy's version of mean value theorem, but I will do that later.